Hello everyone, welcome to Probability and Statistics for Data Science. Up to now in the course we have discussed how to model a single uncertain quantity as a random variable. Today we're going to explain how to model multiple different uncertain quantities within the same probabilistic model. Let's get to it. When we have several different discrete random variables within the same model, we often call them multivariate discrete random variables. Our goal is to model the interactions between multiple uncertain discrete quantities. We do this by representing them as random variables. Remember that we have essentially two different kinds of variables when we're doing probabilistic modeling. Deterministic variables, which we write without a tilde, without a squiggly line on top, and random variables that we write with a squiggly line on top. Deterministic variables have fixed values. They're equal to 2, 3, 23, or whatever. Random variables can have several possible values. They are uncertain. So we describe them probabilistically. We don't say the random variable A is equal to 3. We say the probability that the random variable A is equal to 3 is 0.5. What is a random variable? A data scientist will tell you that a random variable is an uncertain quantity or a variable that represents an uncertain quantity, which we describe by probabilities estimated from data. A mathematician will give you a very, very different answer. They will tell you that it's a function mapping outcomes in a probability space to real numbers. However, we saw that this mathematical characterization is designed so that we can describe random variables using probabilities. So these two perspectives are very connected, as we discussed in the video on discrete random variables. All right, so what's the plan here? We're going to define the mathematical characterization of multiple random variables living in the same probabilistic model. Then we're going to explain how to describe these random variables in practice using probabilities. And finally, we'll explain how to estimate those probabilities from data. In order to introduce the mathematical characterization of multiple random variables, we're going to look at an example. In this example, we have a probability space, which is very simple. It encodes the result of two rolls of a six-sided die. So the possible outcomes have two entries, one for each roll. Each entry can be equal to 1, 2, 3, 4, 5, or 6. So the outcomes are of the form 1, 4, 3, 2, and so on and so forth. Now we can define random variables associated to this probability space to represent uncertain quantities that we may be interested in. For example, a random variable could represent the result of the first roll. That random variable mathematically is a function from the outcome, so it takes in an outcome and it gives you a real number, in this case, the first entry of the outcome. We can also represent another random variable. We can also define another random variable to represent the second roll. In this case, it maps the outcome to its second entry. And similarly, we can represent another random variable as the sum of the two entries. Again, this is a function from the sample space to the real numbers. Why do we want to do this? Why are we defining these functions? Well, this allows us to model the interactions between these uncertain quantities. What do I mean by that? Now, when we generate a sample, or when we choose a sample from the sample space, it fixes the values of all the random variables simultaneously. If the sample, for example, is 3, 1, if the outcome, is 3, 1, then the first random variable is equal to 3, the second random variable is equal to 1 at the same time, and the third one is equal to 4 at the same time. So now we can talk about the probability that the first random variable is equal to 3, the second one is equal to 1, and the last one is equal to 4 at the same time. That's just the probability of seeing that particular outcome, okay? In fact, the whole point of why we go through all of this pain of defining a probability space and then random variables as functions from the sample space to the reals, the main motivation for this mathematically is to be able to encode interactions between random variables in this elegant way. It doesn't seem like a big deal when we have 3 of them, but this enables you, for example, to describe the interactions between an infinite number of random variables, which is not obvious to do in a mathematically coherent way otherwise. That's a little bit beyond the scope of this course, but just so you know that that encoding, or more than encoding, maybe representing interactions between uncertain quantities is one of the main motivations for this definition of the mathematical framework of probability spaces and random variables as functions within those probability spaces. All right, but let's get back to what we want to do, which is understand this mathematical definition a little bit more in depth. Let's remind ourselves of the definition of a single random variable. A single random variable is a function from a sample space to the reals, and in particular, if it's a discrete random variable, the function maps to a certain discrete set which contains all the possible values of the random variable. And what we explained is that we want to be able to talk about the probability that the random variable is equal to each of its possible values. This is the whole point. So in the definition, we actually impose that the probability measure of the probability space has to assign a probability to the events, which are the sets of outcomes mapping to each of these specific values, so that we can talk about the probability that the random variable is equal to A1 or the random variable is equal to A2, and so on. If we look at a picture, what we're saying is that here we have an example where the random variable can be equal to only 3 values. What we're saying is that the event that the event of all the outcomes that map to A1 has to be in the collection, it has to be assigned a probability. And the same for the event of all outcomes that map to A2 and A3, which we're showing here. We explained in the video on discrete random variables that this actually forms a partition of the sample space, and the probability of each of those events can be encoded within the probability mass function of the random variable, which is this function that adds up to 1 and is non-negative and contains the probability that the random variable is equal to each of its possible values. The way we actually manipulate discrete random variables in practice is through the PMF. This is really the user interface, as we said, of the random variable. We usually don't even define the underlying probability space. We just estimate this object from data, and that's what we use to manipulate the random variable. We know that the probability space is there, and we could reverse engineer it if we wanted to, although we usually don't want to, especially if we're doing data science as opposed to more abstract mathematics. So now, basically, hopefully, like that, you get the idea of how the mathematical characterization of the discrete random variable is connected to the object which we actually use to manipulate it, which is the PMF. Now let's see how that works for several random variables. When we have several random variables, here we're going to consider 2 random variables within the same probability space, A, and now we will see B. Each of them induces a different partition, right? Because this is the event of the values that map to A1, this is the event of the values that map to A2. Now if we consider the other random variable, B, it's going to induce a different partition. These are the outcomes that map to B1, these are the outcomes that map to B2. Please notice that this is the same sample space. These 2 random variables are defined within the same sample space as in our die example. Otherwise, we cannot capture their interactions. To capture those interactions, what we're really interested in is what is the probability that A is equal to, let's say, A1 and B is equal to B2 at the same time. We're interested in the intersection of this guy and, for example, that guy. All of these intersections actually also form a partition of the whole sample space, and it's those probabilities that we're actually interested in. Okay, so we're gonna introduce the joint probability mass function, which contains all of those probabilities. The probability mass function gives us the probability that A is equal to, let's say, A1 and B is equal to B1 at the same time. Those are the probabilities of this intersection. So A1 and B1 would be this guy. For example, B2 and A2 would be this guy, and so on and so forth. It turns out that just as in the case of a single random variable, the joint probability mass function completely describes the joint behavior of these 2 random variables in the following sense. Imagine that you're interested in the probability, for example, that A, B are in a certain set of possible 2D values. Let's say A1, B1, or A1, B2. So you can see that when we're describing the joint behavior of the random variables, essentially what we're going to be asking is, can they be in this set of possible 2D values? Okay, and what is the probability that they're in this set of possible 2D values? Well, then it turns out that these sets, almost by definition, we can represent them as unions of these guys. Okay, because here we have a partition of the sample space where each event exactly corresponds to the probability that A is equal to a particular value and B is equal to another value at the same time. So now when we want to describe the behavior of the random variables in terms of what is the probability that belong to a certain set, we can always express those sets as a union of these joint events. So we can add up the probabilities, and those probabilities are all encoded inside the joint PMF. So we can actually discard the underlying probability space and just answer this type of questions. And just answer these type of questions using the joint PMF, and that's what we're going to estimate from data. So essentially, even though there's this underlying probability space, at the end of the day, what we use to manipulate random variables and describe their joint behavior is their joint probability mass function, which encodes the probability that they're equal to every possible pair of values. So we usually write it with a subscript, where here we indicate the two random variables that we're describing. And here in the argument, we say what values they're equal to at the same time. And the joint PMF gives us the probability of that event. And this again suffices to describe the behavior of the random variables completely. So we can forget about the underlying probability space, even though we know it's there. This is an example of a joint PMF of two random variables that have three possible values each. If we want the probability that the random variable A is equal to 2 and the random variable B is equal to 3 at the same time, then it's going to be that probability there, which in this case is 0.05. We can also consider the multiple random variables, as in our die example where we had 3 random variables. And when we do that, it's often kind of convenient to stack them as entries of a vector. We call such vectors random vectors, and we also denote them with a tilde on top. There's nothing very special about a random vector. It's just multiple random variables stacked as entries of a vector. Okay, so you have to think of each of the entries as a separate random variable, which you could call, if you wanted, A, B, C, and D. We can therefore define the joint PMF of a discrete random vector or multiple or D random variables. It's just the probability that each of the random variables or each of the entries are equal to, in this case, the entries of this deterministic vector that we put in as an argument. And usually we have this subscript here to indicate that it's the joint PMF of that particular random vector. When we want to compute the probability that a pair of random variables is equal to a specific set which contains possible pairs of values, we can just use the joint PMF. This is what I explained on the diagram. Why? Because we can express those sets as the union of sets of the as union of pairs, if you want, of the following form, where the first random variable is equal to a particular value and the second variable is equal to a particular value at the same time, and those pairs are within the set that we're interested in. We're going to see an example. I realize how here, I think the mathematical notation makes things look more complicated than they actually are. So wait a moment and you will see an example. It's actually pretty easy. The point is that those underlying, those events are all disjoint, because, if you have this event and then a different event, A1 and B1, unless, well, I don't know what I did there. I lost my, sorry, sometimes I get lost with my iPad. Unless A is equal to A1 and B is equal to B1, these two events are disjoint because each random variable cannot be equal to two values at the same time. because they're disjoint, we can just sum those probabilities, and those are the probabilities that are exactly encoded in the joint PMF. So hopefully this, together with my explanation on the diagram, shows you that you can essentially describe the probability that the two random variables take on pairs of values, or any set of pairs of values, just using the joint PMF. Same thing for a random vector. If we're interested in the random vector being in a set of, if the random vector is of dimension d, this set is going to contain different vectors of dimension d, right? We want to know the probability that x is equal to any of them. When we want to compute that, this is just equal to the sum of the joint PMF over those possible values by exactly the same argument. Again, this is just easier to look in terms of an actual example. Here we want the probability that A and B, to put it in the same notation as we had a moment ago, is in a certain set S. Wow, my handwriting. I'll make an effort there. Is in a certain set S. Here S is the set that A is smaller than 2 and B is greater than 1. So S is actually the set where A is equal to 1 and B is equal to 2, and also includes, so I don't know what I said there, but it's a set that includes two 2D vectors, 1, 2, and 1, 3. Okay, so now if we want to compute the probability that A, B are within this set, then we just sum the joint PMF over the corresponding probabilities, which are 0.4 and 0.5, because this is essentially the union of two events, of AB being equal to this and AB being equal to that. And these events are always disjoint, as we saw, so we can sum their probabilities, and those probabilities are encoded within the joint PMF. Okay, so again, hopefully this makes it clear that the joint PMF completely characterizes the joint behavior of the two random variables. Important properties of joint PMFs are that they are non-negative. Why? Because they are probabilities. And also, if we sum them over all the possible values of A and B, at the end of the day, by our argument now, this just means the probability that A is equal to some value in its range and B is equal to some value in its range. So that's the union of all the possible, of all these events where A was equal to one value and B was equal to the other value. The union of all of those is going to just be the sample space. Okay, so if you want a more mathematical explanation, basically what we're saying is that this has to add up to 1 because we're looking at the probability of the event that any outcome in the sample space happens, right? Because the outcome has to map to some A, B that are in the ranges of A and B. So every joint PMF is going to sum to 1. And it turns out that the same happens for d-dimensional random vectors by the same argument. If you sum them over all the possible values of each of their entries, in the end, you've covered all the sample space. So this has to add up to 1 for it to be a valid joint PMF. Just like a valid PMF also sums up to 1 over a single variable. This is actually enough to be a valid joint PMF in itself. So if you encounter a function that is non-negative and sums up to 1 over all its possible arguments, then this is a valid joint PMF because you can go ahead and reverse engineer a probability space, even though we never do that, in a similar way to how we discussed for a single random variable. So you would just say, the sample space is all the possible vectors that this vector of random variables can take, and then you use the PMF to basically build the probability measure on the power set of all those vectors. Again, not super interesting. You can actually reverse engineer the probability space if a mathematician gets annoying, but we never do this. We just estimate the joint PMFs from data, and that's how we manipulate the uncertain quantities that we're interested in. So we have gotten to the point where now we realized that in order to manipulate uncertain quantities, all we need to do is estimate a joint PMF from data. So imagine that you have a data set like this, okay, where the first entry corresponds to one of the uncertain quantities you're interested in, the second entry corresponds to another uncertain quantity that you're interested in. How are you going to estimate the joint PMF, for example, at 2, 1? Well, here it's just very natural to use empirical probabilities, because what is this? It's just the probability that A is equal to 2 and B is equal to 1 at the same time. How often do we see this? We see this 50% of the time, so it just makes sense to estimate that probability as being equal to 0.5. And it's as simple as that. That's the empirical joint PMF. So here we're considering a quantity that is maybe d-dimensional, and we're saying what's the probability that the quantity that is d-dimensional is equal to a certain fixed d-dimensional vector. In this example that we just saw, v would be 2, 1, where we count how many times the vector value data is equal to that particular deterministic vector, and we divide by the total number of data. Remember that this is an indicator function that is equal to 1 if the data point is equal to v and 0 otherwise. Notice that in order to estimate a joint PMF from data, it's absolutely crucial to have joint observations of the variables that we're jointly modeling. Otherwise, this makes no sense. You have to be able to see the two variables at the same time. Each data point has to consist of values corresponding to the two or the v quantities that you are modeling. Let's take a look at an example. We have a data set of movie ratings where users give ratings between 1 and 5 to different movies. And in particular, we're going to model the joint ratings for Independence Day and Mission Impossible. I'm so old that I still remember when these two movies came out in the cinema, and I watched them in the cinema, both of them. Okay, so here we have the data. These are the ratings for Independence Day, and these are the ratings for Mission Impossible. The actual data that we observe is how many people gave, for example, a 3 to Independence Day and a 1 to Mission Impossible, or a 2 to Independence Day and a 4 to Mission Impossible. And that's what I mean by the fact that you need data points that tie the two quantities that you're interested in together. If we just had separately the ratings for Mission Impossible and the ratings for Independence Day, we wouldn't be able to estimate a joint PMF. Okay, so now from this data, how do you estimate the joint PMF? I would encourage you to stop the video and think about it just for a moment. So what we do is we just divide by the total sum, okay, because that is n if you want. Okay, we already have the sum of this indicator function is just equal to this, because this is how many times we observe this particular pair. Now we need to divide by the number of data points n, and this is what we obtain. Realize that this is in percentage, okay? So this means that 11.8% of people gave a 3 to Independence Day and a 3 to Mission Impossible, okay? Let's take a look at another example where we're modeling precipitation in Oregon. We're interested in the joint behavior of precipitation at 3 locations: Coos Bay, which is by the sea, Corvallis, and John Day. Okay, we want to model the interactions between precipitation in these places. The data looks like this. For simplicity, we're only going to consider data points which tell us where it's raining or not how much it's raining or how much it's snowing. So basically, this means that it's raining in Coos Bay, also raining in Corvallis, also raining in John Day. So this happens 69 times. These are our hourly measurements, okay? So for 69 hours in a year, this happened, okay? It was raining in the 3 places. We can also ask how many times was it not raining in any of the places? 7,253 times. All right. So you can see that these are really the data points that are telling us, the counts of the different possibilities. And now how do you estimate a joint PMF from them? You just normalize them. You divide them by the sum, which is n in our notation, the total number of data points. And you get this joint PMF, which is in percentages. Okay, so about 83% of the time it doesn't rain anywhere. 3.6% of the time it's not raining in John Day, but it is raining in Corvallis, but it's not raining in Coos Bay at the same time. Again, to estimate a joint PMF like that, you need to have data points that tie together the three quantities that you're interested in. So what have we learned? We have learned the mathematical definition of multivariate discrete random variables in terms of this underlying probability space, but we saw that we actually don't need the probability space once we have defined the joint PMF, because the joint PMF completely describes the interactions between these multiple random variables defined on the same probability space. And in fact, that's what we estimate directly from data. And that's all I have. Thank you very much.